Hello, welcome to Silicon Valley Code Campfire. My name is Juval Lowy. We're going to spend the next 20 minutes or so on the Zen of architecture. I will endeavor in this very short session to teach you everything you need to know about architecture and literally to save the rest of your careers. Nothing less will actually do for this session. A few words about myself. I'm a software architect. I'm the founder of a company called iDesign, which I launched 23 years ago, devoted for nothing but software design. I've had some of the most fundamental breakthroughs in modern software engineering of the last few decades. Some of my ideas, like microservices, are obviously household names. I've had several other ideas, including what I'm going to share with you today, which I'm much more proud of. Over the years, we've helped iDesign customers across hundreds of projects deliver great software on their commitments. I published 8 books and more than 100 articles on my ideas and techniques. Before iDesign in the late 90s, I was the chief software architect of a Fortune 100 company in Silicon Valley, and I managed the architecture department. Before that, I was division architect. Before that, just an architect. I'm well into my 4th decade as a software architect. I never worked for Microsoft, but I was privileged to be part of the strategic design effort of key products like C#. Microsoft recognized me as a software legend, something they only gave to 6 people so far, due to the impact they had on the industry over the years. Enough about me, let's talk about this session. What I'd like to show you is the essence of good design, not just software design, but in general design. Unfortunately, if we just start talking about that, it would not make much sense because it is radically different from what you're likely doing now. Now, I'm painting with a broad brush. Maybe here and there somebody's doing it right, but by and large, everybody's doing it wrong. Not just wrong, they're doing it the worst possible way. So we actually have to start first by discussing what not to do. And only once we discuss the what not to do and we nail it to the ground and you say, I can't take it anymore, then we can discuss the what to do. And so by far the most important thing you need to learn is what not to do. And you must avoid functional decomposition. So what does it mean? Architecture is always and everywhere an act of decomposition. You take a big nebulous idea, the system, and you break it down into smaller things. These can be components, modules, subsystems, services, classes. It doesn't matter what it is, it's always an act of decomposition. Functional decomposition is basing the decomposition on the functionality of the system. So if the system needs to do an A or a B or a C, you will have an A feature, a B feature, a C feature. They will have an A block, a B block, a C block. That is functional decomposition, and that is the kiss of death. When you do functional decomposition, the project has already failed, past tense. Before you even write the first line of code, the project has already failed. And yet, this is what everybody is doing. Now, functional decomposition is so bad, I'm going to be throwing you lots of reasons why it's bad. Every one of them is going to be enough to kill it, another nail in the coffin. I will save the best nail in the coffin for last. Only once we discuss the right way of doing things, you will see why functional decomposition is so bad. So let's start with some obvious things. Functional decomposition is always time decomposition because you don't do A, B, C. You do A, and then you do a B, and then you do a C. Which means built into the fabric of a B is a notion, it's called after an A and before a C. Suppose you have another system over there that needs to do a B as well, billing, whatever. And suppose the A and the B and the C are invoicing, billing, shipping. Well, you cannot just lift the billing and put it in another system because in the other system, nobody's doing the invoicing before it and the shipping after it. So the moment you lift the B, the A and the C is hanging off it. And now you understand why none of you has ever reused anything from anybody else. Nobody has ever done in the history of software, of full design system, the following. take a business object, something designed for a particular system, lift, shift, drop it in another system. Cannot be done. Which means functional decomposition precludes reuse, and reuse is a fundamental principle of good engineering. Now, a decent system is not going to have just A and B and C, meaning 3 things. It can have 300 things. If you truly do functional decomposition, now you have a design with 300 blocks. Is a design with 300 blocks a good design? We obviously know it's a bad design. Why? Because even if each one of these 300 is straightforward and simple, the integration cost in any system is non-linear to the number of things that you have. It tends to be even hyper-exponential because it's according to the factorial of the number of things that you have. So now all of a sudden, a system with hundreds of things is impossible to contend-wise because of the integration complexity. The other extreme is pump and bloat. You take this service and you pump into it the A and the B and the C, and you got these 300 things inside it. Now, while you don't have that much of an integration cost, now you have an explosion of internal complexity. And even if you have just 2 or 3 of these things, they are so abhorrently complex, nobody can reason about it. Sometimes you see these things side by side, few monster God objects, and then an explosion of little things next to them, and nobody can maintain these systems. Another problem with functional decomposition is that somebody has to say to the system, do the A, do the B, do the C. Well, who is that somebody? Well, that somebody is the client of the system, say the web form or the web page or the mobile device. But think about it. What if for that customer over there, we're not doing B, we're doing B prime? And maybe for that customer over there, we're not billing, we're extending credit, so we go and do A and C or whatever. All of these things are business logic. And that business logic now must reside in the client. Every developer this side of Alpha Centauri 2 knows do not pollute the client with business logic. 100% of developers are doing it. They must pollute the client with business logic because of the functional decomposition they have to contend with. The client is the one stitching these things. The problem now is, suppose you have this web page, whatever, and then marketing comes to you and says, let's add a mobile device. Well, is it just adding mobile device? No, it's duplicating the business logic from the web page, putting it in the mobile device, and they're all slightly different. Now I have to maintain the business logic in multiple places. And then they want to have still a desktop and maybe some HoloLens and 3D dimensional. All of a sudden, developers throw the hand in the air and they say, we can't take it anymore. We can't have more clients. But the business wants to have more clients and more sophisticated user experiences. Another problem with functional decomposition is as you enter the system to do the A back, the B back, the C back, you've entered the system in 3 places or maybe 300 places. And that means there's multiple places to worry about security, throughput, availability, responsiveness, performance. Now, we all know a good design should minimize the number of points of entry, ideally just 1. But functional decomposition tends to maximize the number of points of entry. I can prove to you that functional decomposition is the wrong way of designing any system without using a single software argument. I'm going to refer to the first law of thermodynamics. The first law of thermodynamics simply states that you cannot add value without sweating. Now, we don't know why this is the first law of thermodynamics, but we know that on this side of the Big Bang, that's the way things are. Before the Big Bang, inside the singularity, maybe the first law of thermodynamics does not hold, but on this side of the Big Bang, that's the way things are. Why? We do not know. In fact, the only way to define the moment of creation is the moment that the first law of thermodynamics kicked in, which basically means you cannot add value without sweating. Why? We do not know. There is nothing in Newtonian physics that mentioned the first law of thermodynamics. It took Lord Kelvin a little bit more than 100 years ago to phrase the first law of thermodynamics. Now, suppose you're doing functional decomposition, and suppose I'm giving a requirement spec for the system. It can be a nice document with 1 is A, 2 is B, or maybe a set of sticky notes on a Kanban board with A and B and C sticky notes. And I say, design me a system. You say, no sweat, A service, B service, C service. And that's the problem. You said no sweat. Now you're trying to cheat the first law of thermodynamics. Now you're saying, on one hand, I'd like to have I'd be a highly paid individual and get a lot of salary. And I'd like to do architecture because architecture is an added value activity. On the other hand, you endeavor to cheat the universe by trying to do it without sweating. And that is simply not going to happen. So here, without using a single software argument, I prove to you that functional decomposition, by the nature of the universe, is precluded from ever working. And yet, that is exactly what everybody is doing. Why? It's the allure of the free lunch. Human beings cannot resist the allure of the free lunch. Now, we all know there is no free lunch in the universe. But functional decomposition, of course, pretends to be free lunch. It's so easy. That's my architecture. Now, because human beings cannot resist the allure of the free lunch, you always do functional decomposition. This, by the way, has nothing to do with intelligence. For thousands of years, the smartest people in any kingdom were the alchemists. The alchemists were trying to convert base metal like lead or nickel to gold. They commanded king ransom. They produced exactly 0 results, and yet for thousands of years, people kept trying. People cannot resist the allure of alchemy, of free lunch. And again, this has nothing to do with intelligence. The greatest alchemist of all time was Isaac Newton. Isaac Newton spent 2 years writing Principia Mathematica, and he spent 22 years trying to figure out the Philosopher's Stone. Your developers are not smarter than Isaac Newton. This has nothing to do with intelligence and everything to do with human nature. Human beings are attracted like moths to a flame to functional decomposition. The correct way of designing any system is to decompose based on volatility. These 4 words, decompose based on volatility, is everything you will ever need to know about any kind of design. The idea here is that you strive as an architect to identify areas of potential change in your system. Those you encapsulate in services, modules, components, and then you implement the required behavior of the system as the interaction between these encapsulated areas of volatility. This is the only way to design, by the way, any system. Everything around you is designed this way. For example, let's talk about pumping blood. Pumping blood is incredibly volatile. High blood pressure, low blood pressure, running, sleeping, with adrenaline, without adrenaline, dehydrated or not. And yet, all of that volatility is encapsulated right here in a component called the heart. If I had to worry about pumping blood right now, I could not deliver this session to you. I can drive your car and you can drive your car. Now, you can drive my car. Now, unless it's a complete clone of each other, there isn't a single reusable component. You cannot reuse my carburetor or my gearbox or anything else. So there's enormous volatility between these 2 cars. However, the reason I can drive your car and you can drive my car is because the volatility is encapsulated. It's encapsulated behind the dashboard and the accelerator pedal and the brake pedal. So in all good systems, we always encapsulate the volatilities. Now, if you were to implement a car, the car has a feature, take you from A to B, but there is nothing in the car that takes you from A to B. You implement the feature of the car by integrating areas of volatility. I'm giving you now this session by integrating areas of volatility. We discussed the heart, but there's also a liver that encapsulated the volatility in metabolism. My laptop encapsulates the volatility of what it means to store the PowerPoint file and also to stream the network. And my internet provider encapsulates the volatility of what it means to connect to the internet, and on and on and on. That is the only way to design anything. The reason this works so well is because when you start using volatility-based decomposition, you envision your system as a series of volts. Every volt encapsulates an area of potential change, a very risky change. Now, when a change happens, it's always a negative thing. It's like a hand grenade. What do? You open up the appropriate volt, toss the hand grenade inside, and close the volt. And the volt does poof. Now, whatever was inside the volt may be completely destroyed, but there's no sharpener flying all over the place, destroying everything else. Put differently, you've contained change. And now we finally understand what is very bad in functional decomposition. In functional decomposition, because you decompose based on functionality, by definition, the change cannot be in any one place. And so now, when a change does happen, it is like swallowing a live hand grenade without the pin. And now when a change happens, it detonates everything and shreds everything. And good system design must be resilient to change. Change is good. Change is what keeps all of us employed. If the world was static, none of us would have a job. We are here because things change, because requirements change, because the world is dynamic. Volatility-based decomposition doesn't resonate with the change. It contains it. Functional decomposition maximizes the impact of the change. All the other things I said about it, that was enough to kill it, like 300 blocks and monster monoliths. But what about this? Now you understand all the horrible things that have happened in your past systems. Now you understand why all of these systems have what you call technical debt, why you cannot introduce changes. All the developers in the universe are bitching and moaning about technical debt. Nobody stops to ask the question, why do we always end up with this technical debt? Was it written in the firmament that we should have technical debt? No, it's because of the nature of the architecture. If you do functional decomposition, you will always, always, always suffer from inability to introduce change. Furthermore, something else is happening. If indeed this is your architecture and you can contain changes, that enables you to respond quickly to changes in the business. The ability to respond quickly to changes in the business is the essence of agility. Every developer on the planet said the word agile and agility bazillion times. And yet every developer and architect on the planet has most likely done everything in their power to deny agility. Because when they do functional decomposition, they completely and utterly guarantee the lack of agility. They've maximized the cost of the change. They've maximized the lack of ability to respond quickly to changes. Now, these are universal observations. You will see it when you design an airplane, a house, a laptop, it doesn't matter. But we're not in the business of designing airplanes, we're designing software systems. So you can ask yourself the following question. Are there typical areas of volatility in a typical software system? And if there are typical areas of volatility, are there typical interaction, typical relationships, typical do's and don't, typical cardinalities and things to look for? And the answer is absolutely yes. In fact, the hallmark of good architecture is that it holds true regardless of context. For example, a mouse and an elephant have the same architecture. Now think how different a mouse and elephant is as far as size. There is nothing in the detail of a mouse and elephant which is the same, and that they have the same architecture. Why? Because there's something very good in that architecture. And so in most business systems, you can identify these overarching architectural concepts. And I've developed a methodology around it. I call it the method. It's a template, it's a mental machinery for identifying areas of volatility. Think of it as a good start point. In a typical software system, you will typically have these areas of volatility. Now your management will vary, maybe you have more of this and less of that, but it's a good starting point. It also provides good runtime relationship and templates. These things typically do it like this. The first thing to also observe is that good systems are designed in layers. And the reason we like to use layers is because layers layer encapsulation. Each layer encapsulates from the top what happens below. Now, the method gives semantic for the layers and identify what is going on. The top layer, we call it the client. Sometimes you hear the term presentation. I don't like the word presentation because it implies there's a human in the loop and somebody is clicking buttons, and maybe some information is indeed presented, but perhaps this is just an API for another system and there's really no user involved. Ideally, you want to equalize all clients to be the same, meaning regardless of client technology, web page, mobile device, API, they're all clients of your system exactly the same way. Put differently, You both advocate a single point of entry here, but also you allow each client to encapsulate the client technology volatility. So what this layer encapsulates is client volatility. Underneath that, we have the business layer. In the business layer, encapsulate business volatility. Now, business volatility expresses itself in changes to the requirements. The best way of expressing requirement is use cases. Use cases are simply sequencing of certain activities, and basically they describe the required behavior of the system, not the required functionality of the system, the required behavior. Now, if you're supposed to encapsulate volatility in the use case, what form would that volatility take place? And so it turns out that the business has only two types of volatility. There's sequence volatility and activity volatility. What does it mean? Suppose I have a use case that is doing three activities, A, B, C. Well, how are you going to do this A, B, C? Well, you can do it like this, or like this, or like this. So even though I'm still doing the A and the B and the C, there's enormous volatility in how I'm orchestrating it, in how I'm sequencing it. Since the sequence is so volatile, you need to encapsulate it. The entity that encapsulates business sequence volatility, I call managers. Managers tend to implement a family of logically related use cases. What is logically related? That's up to you. You decide what it means. Grosso modo, they tend to map more or less to subsystems. But there's another more subtle volatility in the business. I could keep the sequence, but drastically change the activities. Look at this. These are two identical sequences, but they use different activities. In fact, B can evolve to B prime and then becomes a D and so on when nothing actually changes in the sequence. So the activities can be volatile independently of the sequence. So the other entity in the business is the engine. The engine encapsulates the volatility in business rules and business activities. It's how this customer wants to do this, is how that customer wants to do it. Now, because I can always change the sequence without ever changing activities, we said that managers can use 0 or more engines. Engines can be shared between managers. There's nothing wrong with reusing it. Now, underneath that, we have another layer which encapsulates resource access. Now, your system is going to have resources, queues, files, databases, caches, local, remote, cloud. And so there's enormous volatility in how you access a resource. For example, how many ways you have of accessing a database. And unfortunately, none of them is superior to all the other ways. And if it's a local database versus a remote database, I access them very differently. And the way I construct things is very different. So it turns out that accessing a resource is volatile. Now, most people did not miss that point, but what they do is when they try and encapsulate the resource access, they expose CRUDs and IO. So they do select and set delete. That is a really bad idea. The correct resource access does never expose the CRUDs, because when you expose the CRUDs, you betray that the underlying resource is a database. If all of a sudden I want to switch to cache, then my select and set delete is toasted, and then everybody upstairs detonate. Good resource access exposes the most atomic business context or atomic business verbs. So what does it mean? If use cases are sequencing of activities, those activities can be use cases on their own right, which in turn can be use cases of other activities. And you can keep breaking it like this, but at some point you will discover certain activities which are so atomic, so primitive, there's no way of expressing it in any other business context. So the resource access exposes that. For example, if I have a bank and I have a use case to transfer money between two accounts. So how do I do it? I credit one account and I debit the other. Therefore, transferring money in a bank is not an atomic business operation because I can express it using other operation. But credit and debit are atomic business operation. There's no way of expressing it using anything else in the bank. Now, the beautiful thing about atomic business verbs is that they don't change as long as the business doesn't change its nature. So if you look at banks, since the time of the Medici, banks need credit and debit. And so credit and debit are atomic business operations, as long as the bank is in the banking business. If they move into ballistic missile control, credit and debit are not that useful, but how often does the business change its nature? Not that much. So what you need to identify is those atomic business verbs, and then you expose that on top of the resource access. And resource access becomes a transformation function between atomic business verbs and actual CRUDs. So now, if you move between database and a cache, only the transformation function inside the resource access changes. Nobody upstairs needs to know about it because they just consume atomic business verbs. And you've encapsulated this volatility. Underneath that, we have the actual resources, the physical queues, the physical databases, and so on. And then we also have utilities, infrastructure, which is common across all systems like security, message pass, pub sub, diagnostic, instrumentation, profiling, those things. So conceptually, the way to think about any system looks like this. We've got clients at the top, managers, engines, resource access, resources, and to the side, we have all these utilities that everybody needs to use as part of the framework. A good litmus test if something is a utility or not is, can you use it regardless of the business system? Can you use it in this system and in a cappuccino machine? The answer is yes, it's a good utility. We're running out of time here, but you can put on top of it a layer of interaction. How do these things typically interact with each other? What are managers allowed to do? Who is allowed to call whom? Can managers call other managers under which conditions? Who is allowed to call down or sideway, and on and on and on. And once you build this mental machinery, the design becomes an unbelievable act, because all of a sudden you encapsulate the volatilities and you have a design that can withstand the test of time. Many times I've put into production systems that were good for decades, plural, decades. 20 plus years later, we will come to it, yeah, design still works, technology comes and goes, the architecture stays. That is the hallmark of a good design. For those who want to learn more about these concepts, let me refer you to my recent book, Writing Software. Note the homophonic, writing, as in standing up correctly. The book has two parts. The first part is about system design, and the second part is about project design. Much as you design the system, you must design the project to build it. And the book marries these two concepts together. You can also find information on the Edison website on the masterclass I conduct. The Architect Masterclass of 2024 is going to be in March next year in California. And with that, thank you so much for your time, and back to you, Peter.